Okay, so a quick little mic check here. Sounds pretty good. All right, so welcome back to, I think this is phase 3 of our slowly building up Atari 5200 game. So I've got some really interesting stuff planned for today, and I'm hoping that by the end of today we'll have something that actually looks like a game. That's kind of what I'm hoping for, so we'll see if we can pull that off. But I think before we start doing anything new, let's first look at what we already have. Where did we leave off? Just a quick review of, if I can type today. Not a good start, huh? All right, it's a quick review of where we are. So this is the screen we left off with. And what we have here, we see there's some junk up in the top left corner, and we got this square, or box, or whatever it is. So that box there is player 0. That is a sprite. That's an object. And we had it rigged up so that we could move it left, right, up, and down with the joystick. Very nice. Now this garbage up here that I'm moving toward, this is playfield. I believe at the time I was demonstrating playfield mode E, which is 160 pixels across. This is a bitmap mode where it just reads pixel data directly from memory and displays it on the screen. This mode has 4 colors. There's the background color, which in this case is black. And here I have 3 more colors that I'm showing. This kind of orangish color and the kind of greenish color and the kind of pinkish purplish color. I think this is, I don't know, two or three lines of mode E, because each line of mode E is a single scan line. So that's what we're displaying here. And I think I was just demonstrating mode E. That's a bitmap mode. So let's talk a little bit about where we're going to go from here. So I want to start putting together an actual game screen. And earlier today, I went ahead and prepared a background image. And I'm not going to go into the details of how I prepared that image. I'll suffice to say I just used GIMP and converted it to a 4-color image, and then, okay, I guess I'm going to go into the details of it. I used GIMP to create it. I converted it into a 4-color indexed image and then output it as a C file, and I then wrote a little C program that read that graphics data and converted it into the format that the 5200 expects. So this has already been done. Creating graphics for this system is one of the more difficult things, and if you're going to do it, I suggest looking around, seeing what tools are available, and figuring out how to do it. That's not something I'm going to do here on stream because it's a very tedious operation. But I will show you the file that we came up with. I also want to say I have not yet tested this file, so maybe it doesn't work. So I created this file called background.s. This contains just a big pile of data. So we've got org B000, or is that, excuse me, 8000. Starting at address 8000 hex, calling it background, and it's just byte after byte after byte. There's tons of data in here. So this is all data for a single background image that I created. Now, I based this image on the background from the Intellivision version of Demon Attack, which I always thought was a really cool background. I think the TI computer version might use a similar background. But the first thing I wanted to do today is to try to get this background up on the screen and work through some of the problems you're going to get through with a large-scale Mode E bitmap. So let's look at the code. Now, if we're going to display this bitmap, we need a display list that is capable, a display list is capable of displaying it. And we have a display list here somewhere that we were working with. Here it is. So what I'm planning to do here is I want to have a line of mode 2 at the top. That's the 40-column text mode. And I want to have another line of mode 2 at the bottom, another 40-column text line. And then we're going to put this bitmap in the middle. It's going to all be mode E. Now, the text line at the top, I figure we can use for a score display or something like that. The text line at the bottom, not really sure what to do with that yet. We'll figure something out, but I want to have it there just to be available. We can do something with it. And if we don't like it, we can always change it. So the visible screen area on an NTSC television is 192 scan lines. A line of mode 2 is 8 scan lines high. So we have one mode 2 line at the top, one mode 2 line at the bottom. So we take 16 scan lines out of that 192. And that gives us to what, 176? Yes, 176. So our display list is going to be a line of mode 2, 176 lines of mode E. It's going to be a big display list. And then another line of mode 2. So this is going to be a titanic display list. Now I'm going to put the display list in the ROM. I'm just going to build it right here on the screen. But this is the sort of display list you might want to actually create in RAM, because it would take up a lot less space to write the code that would create this list than it would to actually write the list. But for the sake of simplicity here, I'm just going to put it into the ROM. Now, display lists in RAM are fairly common because sometimes you need to make changes to the display list from frame to frame. So it really depends on your use case and what you're doing. Sometimes the display list, you'll keep it in the ROM. Sometimes you'll have to do it in the RAM. It depends. Or your combination of both. I actually have a display list in Robin Banks that starts in the ROM and then jumps into the RAM. So there are a lot of different ways you can do it. We're just going to stick the whole thing in the ROM, though. So let's start clean here. I'm going to start fresh. So we have our 70-70-70. That's our overscan area. So we're going to start with, like I said, we're going to start with the line of mode 2. But being that this is the first line, we need to give it an address to start reading graphics data from. So I'm going to point it at address 2000 hex, which I believe we might have the hello world string still sitting there. Maybe. Or did we overwrite that with the graphics data? I don't remember. Either way, that's where I'm going to put it. So we're going to have a line of mode 2 at 2000 hex. Then we're going to switch to mode E. But we need to repoint the data here. So we need to point somewhere else. So I'm going to point to the data in the ROM for that giant background image I just showed you. And I believe I said that was at... All right, that's at hex 8000. Now, you know what? I can write this way. I can say... Okay, just to sum up again. So this is the graphics mode. The 4 here means the next 2 bytes that follow are going to be the address where you're going to pull your graphics data from. So here we did a line of mode 2, which is 40 column text, followed by the address to read graphics data from, which is, and it's little endian, so the least significant byte comes first. So we're looking at address 2000. That's where it's going to start reading from. Then we're going to switch to a line of mode E, and we're going to give it a new address to read from, which in this case is 8000. However, I named that address. So I think I'm going to use the name instead. We're going to use the word directive here because it'll get the ordering correctly. And I just named it background. So we're going to put background here. That way I can move that address around if I need to, and I think I might end up needing to, without having to mess with the display list, because it'll just refer to that particular location. All right, so there's one line of mode E. Now I said I needed how many? I said 172, I think, was the final total. No, 176. Yeah, 176. So we need 175 more lines of mode E. So this is where copy and paste comes in handy. So we'll do 5 at a time. You know, actually, I think we'll do 10 at a time. So mode E, mode E, mode E, mode E, mode E. That's 5, 6, 7, 8, 9, 10. Okay, there's 10 lines of mode E. Now we need 176 lines of mode E. We already have the one up there before background. So now at this point we have 11. So losing counter. All right. So I need 176. I've got 11. Which means I need 165 more. So I'm going to make 16 copies of this line. Now I'm going to make 17 copies of this line. And I'll take the last 5 bytes off. All right, so if I've done the math right, that's 176 lines of mode E right there. And then I said we wanted a mode 2 line at the very bottom. But we're going to change the memory pointer here again to go back into the ROM. Now I'm going to go to address 2028 hex. And the reason I picked that address is because it's 40 bytes after the address of our first mode 2 line. So every line of mode 2 takes up 40 bytes because it's 40 characters. Similarly, every line of mode E actually takes up 40 bytes as well because the data, it's 2 bits per pixel. So each byte contains 4 pixels worth of data. 40 times 4 is 160. So 40 bytes after this top line, we're going to have the text data for the next line. So we'll just put it together in memory. It'll be nice and convenient. All right, so let's go ahead and run this and see what happens. Now, I expect we're going to see part of the background image. And I'll explain why. Oh, I forgot to set colors. But we have colors. Okay, look at that. We got something. We definitely got something. Okay, so we need to set the colors correctly. Now, unfortunately, I don't remember which color was which in my image. I think I do. Okay. So we need to set some colors here. Let's find the colors. Where are the colors? Where are the colors? Color background. We'll leave player missile 0 alone. Here we go. Color 1, color 0, color 1, color 2. All right, so color 0, I believe we're going to want to be kind of a gray color. So we'll make this 0, I don't know, 09, 08. Color 1, I think, is going to want to be kind of bluish, maybe. So let's find blue. All right, 7 and 8 are both kind of a blue, so we'll go with kind of a bright blue. So we'll go with like 7A. And the last color I'm going to want to be greenish. Looks like C, so we'll go with CA. All right, so let's see what happens here. Actually, okay, it looks like I did put the background stuff there. Okay, we're going to clear out this. This was writing to, that was setting up that little Mode E demo I had. We're going to get rid of that. Okay, so let's see what we get now. Woo, boy, that is not what I was expecting. That's not what I was expecting at all. Okay, so something is clearly wrong here. What have we done wrong? Well, we're reading a bunch of garbage. Oh, you know what I did? I forgot to include the file in the program. the new file. Okay, so we're going to go... I have to include the new file, so I didn't do that. So it's just... In fact, how is it even building? It doesn't know where that address is, does it? Anyway. Okay, so down here, somewhere, where are we going to put it? We get rid of this hello world byte. All right, so we put that at address 9000. It's got to go before this because you can't go out of order. So right here, we're going to include background.s. I wonder how it's resolving that background label. I don't know where that's coming from. Unknown mnemonic background. Okay, I have clearly screwed up somewhere here. Oh, I already had a background. What was that? Oh, that was that test thing I did. Okay, that's why it was working. All right. Okay, something's wrong in the background file. We'll fix it though. It's useful to see these problems as they happen. Why does it think that's a mnemonic? That's a label. Why is it not recognizing that as a label? I'm not sure why it's not recognizing that as a label. That's a little weird. Okay, maybe I just got some garbage in here I don't realize. This is an auto-generated file. It's possible I screwed it up a little bit. Okay, it's saying the error is at line 188. Oh, I have to indent that. Duh. There we go. All right, now let's see what we got. Okay, look at that. We got part of it. Now, gosh, I'm going to have to do interrupts faster than I thought, wasn't I? You know, we'll come to that. So what I try to do here, and you can see it's kind of broken, is on Demon Attack for the Intellivision, there's a kind of like a lunar surface on the bottom, like a dome lunar surface you move on top of. There's a planet Earth to the right, and then just all stars in the back. And you can see it started to do that. My colors are off, but we can fix the colors. See, here's the planet that I was starting to put in. You got the stars out here, but something's going wrong right around here. Something's going very wrong there. And I'll tell you what's going wrong there. So there is an issue with Antic when it comes to large images. And this can be really tough to resolve, and it's why I knew this was going to happen. I made this mistake on purpose because this is something that catches people out. It still catches me from time to time because I forget about it. Before I get to that weird Antic problem I'm going to describe, I want to talk about this up here. So the way colors work for text modes is really weird, and these colors are clearly wrong. So we're going to need to do some other tricks here, which I didn't anticipate doing this early. In fact, I might skip them for now, but I knew I was going to have to do it down here. I forgot about up there, but we'll get to that. So my colors are a little off here, but it looks like we're pretty close to what I want. But we need to solve this problem. So what is the problem? What is Antic doing here? Why is it screwing up this image? So when you give Antic an address to start drawing from, like we did right here, we gave it background. We said start at this address, 8,000 hex, and start drawing whatever data you find there. For whatever reason, as Antic moves along, it cannot cross a 4K page boundary. So when you're talking about hexadecimal addresses, 4K page boundary is that digit. As soon as it hits address 9,000 hex, it doesn't go to it. It just rolls over back to the beginning and starts displaying 8,000 hex again. So I remember reading once what the technical reason for this is, but I honestly don't remember what it was. I'm sure somebody can tell me, maybe. But the way you need to fix this is you need to do another memory load somewhere in the display list to get Antic pointed to the right place. And we might also need to realign this stuff a bit to get it working right. Because you got to play these games sometimes to get large images to work. And it's unfortunate, but it's just one of those things you got to do. So the first thing we need to do is to figure out exactly where the break is. At which point is this just failing and resetting? Now we should know, actually, because it's when the address rolls over to this. So it's going to be 4 kilobytes after that. So whenever we get to address 9,000 hex, that's when it breaks down. So the question then becomes, at what row is that going to happen? Because that's the row where the problem is. So every row is 40 bytes. Well, we got one right there. There's 40. And we do 10 more. So at this point, we're at 440 bytes, 840 bytes, 1240 bytes, 1640, 2040, 2440, 2840, 3240, 3640, 4040. This is where it's going to break down. Actually, this one's fine. This is where it's going to break down. I think, so 4040. This row will be fine. That's 4080. This is the row, I believe, where it's going to start going crazy. Because it's going to hit 4096, which is the 4K boundary, and then it's going to loop back to the beginning. So this is where we need to make our fix. So what I'm going to do is I'm just going to move this down to a separate line, just so we can visually distinguish it. Okay. Now, to test this theory, I'm going to, here's what I'm going to do. I'm going to remove, I'm going to comment out all of these lines. I'm just going to leave that mode 2 down there. So let's see what it looks like now. Okay, so you can see where we stopped. So this is approximately 4K into this image. Now, how big is this image? So it's 160 pixels wide, but that's 40 bytes. So it's 40 bytes per row. I'm working with a calculator right now that you can't see. 40 bytes per row. We said it was 176 rows. So this is 7,040 bytes. So this is almost an 8K image. It's a big image. This background image would take up a quarter of a traditional 5200 cartridge. I mean, this is a serious image. In any real project, I would compress this and copy it into RAM. But here, just for the sake of simplicity, I'm just using it raw. But we're going to need to break this up. So let's go back to here then. So this is 40 bytes. This is right before. So this, if this was 40 bytes, this is 40 bytes right here. So after 40 bytes, we need to break up this image. So here's what we're going to do then. Here's the first row. That's 40. So line 3 is 40. So let's just count it. 40, 80, 120. No, that's stupid. All right. So every 10 lines is 400 bytes. So if we want to go forward 4,000 lines, we want to go forward 400 lines. Or 4,000 bytes, we want to go forward 400 lines. So I'm guessing line 403 oh wait, there's an, oh no, never mind. Wait, this is 40 bytes. 40 bytes. Okay, my math brain is failing here. So where would the break be? We need, if each of these is 40 bytes, then 100 lines is 4,000 bytes. So if we go to line 103, okay. At this point, I think we're 4,000 bytes in. So this would be 40. Which means this, I believe, is the row where things are going to go haywire. Now, I want to put some data in here to test this out, just to make sure we're on the correct row. So I'm going to put another 0E in here. All right, I'm a little sniffly today. It's a shame. I have to go host a game of Magic Realm tomorrow. Okay, so we're going to put another 0 right here, because we got to be precise with this. We got to make sure we hit the exact spot to do this. And this is annoying, but it is, unfortunately, the way it works. Okay, so you can see we did hit the correct line. Because you can look here, if you look just above the green bar at the bottom, you can see there's a black line there. That's where it is reset. It's gone back to the top. So this is the correct line. So here's what we're going to do. All right, so how many lines have we got to go in then? I guess count this right. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 102. And I'm on line 105. That's exactly where I need to be. Okay. So I'm going to test something here. I'm going to change 3 bytes to FF. And I just want to see that if this is the row we're thinking of, because those FFs should be pretty plainly visible now. I just want to make sure this is the right row. Then we'll fix this thing. There they are. See right there? Those are the FFs. You see a little line there. So this is the correct row. So this is the row where the break happens. So we need to fix it right here. So how are we going to do that? Pretty easy, actually. So as it turns out, well, first of all, well, you know what? I'm going to take take 2 0E's off the end here. And they're both going to live in that row. Put this one back on there. Okay. So Here's what we're going to do. At this point, we're going to do another memory change because this is where the break happens. We're going to point it to hex 9000. And then right here on this row, change it to org 9000. Now, if we run this now, we shouldn't see that break on the planet there. We're still seeing the break. Okay. I screwed up. Am I off by another line or something? Okay, so what did we miss? Okay, let's undo the org statement and change this back to a plain 0E. I want to look at this again. I thought I had the math right and everything, but it looks like I didn't. This is unfortunately something you got to do sometimes, just trial and error and trying to get the byte counts exactly right. And I wish my cat would stop yelling at me. I don't know what she wants. Okay, so there's those zeros I put, those FFs I put in pretty clearly. And then we have this break right here under the planet. So this must be the right line. This is where the reset is happening. It all lines up. I don't know why it's not working. Let me take a look at it again. Oh, now it looks like it worked. Oh, now it worked. I must have forgotten to save a file or something. Now it works. Okay, we're good. Okay, so here's what I'm going to do then. Now we're going to uncomment all of this. And now we should have the whole image. Bam, look at that. Okay. So the colors are wrong, but this is the image I created earlier. So this is those test bytes I put in. So this is the line where it breaks. So this is an important thing to remember about Antic. The Antic's internal data pointer cannot cross a 4K boundary. Now, with some graphics modes, this will never be an issue. It mostly comes up in bitmap modes like mode E here. This is where you run into the problems. And I expected to run into that problem, and I actually wanted to show that and solve it because it's one of those gotchas, right? That you'll get it, and you'll get that problem and be like, oh man, what is going on here? Now, what I'm not understanding is why these colors are not where I expect them to be. But let's fix them. Okay, so let's get the colors right, and then we're good. So, you know what? I don't know what color's which. Let's see. So, if we look here, this is the bottom. This is the moon. So, I want this to be kind of a gray color. So, byte FF, remember, it's 4 bytes per pixel. No, 4 pixels per byte. The other way around. 2 bits per pixel. So, an FF byte is all ones. 2 ones means color number 3. Or 2, excuse me. It's 0, 1, 2. There is a color number 3, but that's a special color. So, these blocks down here, this is rows of 4 instances of color number 1, which is this bottom moon surface. So, or color number 2, excuse me. So we want color number 2 to be kind of a gray color, and I do have the wrong color there. Yeah, I think I got these ones backwards. We'll make this CA. We'll make this 0, 8, or whatever I made it. It's just a gray color. We can tweak it. Boy, that's ugly. Where is this green color coming from? That doesn't look right to me at all. Am I getting my color codes wrong here? Oh. I put the numbers in the wrong place. Oh, yeah, dumb stuff like that happens all the time. Okay, that's a little closer what I'm looking for. I kind of want this color back here to be blue and this other one to be kind of like a brown color, but we'll get there. So the moon's fine, though. So the moon and the stars are all the same color. They're kind of a grayish color. I thought about putting little craters in the moon and with the background color, but I just didn't get around to doing that. That's an embellishment you can do if you feel the need to decompile it. So I'm going to reverse these two colors. Although we're going to make some of them darker. You know, let's... I think they're too bright. They need to be darkened, but let's make sure we get them right. Okay. That's closer to what I was looking for. There's our little moon with Earthscape. I'm going to get rid of that test data I threw in there before I forget. Where was that? Crap. It was at Org 9000. Okay. So I think I'm going to darken these colors a bit. This is always tough because how these things look on an emulator is not always how they look on a TV, and it gets a little rough sometimes. And you don't want them to clash with the objects that are going to be on top of them, but that's a little bit better. I think I might want the moon darker too. Problem is the moon and the stars are the same color, so if I darken the moon, I darken the stars too. But that's just life. Okay. You know, I think this is probably acceptable. This is probably a decent start. Okay, so check that out. I mean, this is actually starting to look like a game now. We got a background with a planet and a moon and some stars, and we got some crap going on the top and the bottom that we'll get to eventually. Those will be text lines. So now we need to do something with the player. Now, something I forgot to mention, there's actually a weird thing that goes on with player 0 where there's a mode where if it overlaps some of the colors, it kind of mixes with them. You can kind of see it happening here. We need to fix that. And I believe you fixed that. Okay, there's a register called prior. It's for the sprite priorities. I've mentioned it before. And that's a prior thing. I think I'm going to put... I'll put it up here. Although, you know, I might want to play with prior. All right, so I believe priority number 1 stops that feature. I didn't know about that, actually. And I think it was Real Sports Curling. The game I did shipped with that active, and I didn't realize that's what I was doing. Okay, so if I did that correctly... You won't, okay, yeah, I think it's not doing that mixing now. I mean, it's kind of tough to tell, but yeah, that's definitely different. So there are different priority values that give you different ordering between the background colors and the sprites. So if I play with prior, I could get a priority where this guy would go like behind the screen or something. There's a chart you can find, I think it's in Wikipedia. Prior is a function of GTIA. If you go to the GTIA page on Wikipedia, you can find a listing of all the priority settings. I'll just throw 2 in there and see what happens. I just want to get one that shows this layering effect just to do it. And I don't feel like actually going and looking up the chart. But now we're in priority 2. And let's see. Okay, that didn't affect this one. It might affect a different sprite because the different sprites have different priorities. Let's try 3 and see what that does. Sorry about this segue. I just want to show this off while I'm thinking about it because I don't think we're really going to be using it in this project. Got it. You know, the problem is that player 0 is a very high priority sprite, so it's hard to find a priority setting that's going to actually put it behind anything. So you know what? Screw it. I'm going to go to Wikipedia and look it up. So I just search for Atari GTIA, and you'll find the Wikipedia page, which has a complete breakdown of all the registers and how you set them up. It's actually quite useful. It's a very good reference. There's a similar page for Antic that I often find myself referring to. Okay, it looks like priority 8 should demonstrate this. Okay, so priority 8 will demonstrate this layering effect. Now, not every layering possibility is represented on the chip. There's just too many. But there's a set you can play with. You usually find one that works the way you need it to. There we go. You see how the sprite is disappearing behind the bluish lavender color there? So that's the effect that the priority register can have. And this allows you to create things like foreground objects. But they just have to be a certain playfield color for this to actually happen. Sorry about that. Like I said, I'm a little sniffly today. Not sure why. But yeah, that's the effect of the priority register. Am I going behind the green too? It looks like I am. Okay, so I'm behind the blue and the green with this priority. But not the gray. Yeah, so you see, this puts 2 colors ahead of player missile 0. And the moon is the only thing that is in front of it. So yeah, you can get kind of a weird layering effect of this if you play with it correctly. But we're not going to do that right now. So we're going to put 1 into priority, which is all players and missiles on top of the playfield. And none of that weird color mixing that tends to happen. So we can close this now. We're done with that. Now, let's talk about what we're going to do next. So at this point, we have a cool background. And we need to do something with the player. So I want to turn the player into something cool, like a spaceship or something. And it's going to move down here on the moon and shoot it. For the moment, we'll just have horizontal motion for the player. We might play with vertical motion later. I'm not really sure. But first thing we're going to do is give the player a cool look. We're going to change what he looks like. Okay, so here's the player sprite. Right now it's just this box. Now, this top row of zeros and this bottom row of zeros, those are there to make vertical motion easier because it'll kind of erase it as it moves up through memory. I'll leave those there for the moment. Okay, so we're going to have a 16 pixel tall player with the 2 padding zeros. So, we just make some space. Okay, so here's our sketch board. Now, it can be useful to have an odd width. Well, the player's always 8 pixels wide. There's nothing you do to change that. But it can be useful to only use 7 of those pixels because that allows you to have centered features. So if you use all 8, you can't center anything because it's an even number, which, is kind of tough. Anyway, so I think I'm going to do a 7 pixel wide player so we can center it. So I'm just going to ignore this last row of zeros. So let's put a 1 here. We'll have like a pointy, like a pointy top, like a Galaxian ship or something. And I don't know. I'm not an artist by any means. We'll spread out a little bit. Maybe we'll go really wide here. We have a couple little prongs coming up like this. Yeah, that's going to be cool. And then we'll do that some more. Maybe it's a little narrower right here. For a couple rows, so we'll make it narrower. And then it'll go out again. And then maybe it'll like go down like that. There we go. That's going to be our little player ship. So let's see how that came out. Oh, look at that thing. It looks like a turtle. I like it. It looks like a turtle. I'm fine with that. I think I want to put it, I don't know, maybe about right here, because I don't want to get too kind of lost in the planet there. There's our turtle. All right, this is our space turtle. We could probably stand to make him taller, but, you know, for the moment, let's just run with this. Now, the next step is to give him a decent starting position. So here's what we'll do. Let's figure out where I set that starting position at. Player X. Well, X is easy. That's the center. I don't know what's the center. You know, what am I using now? 80? Let's go to 120. It's Y I'm worried about. All right, so here we go. Player Y. So we need to move him down to get him onto the moon. So higher numbers are further down. So we'll go down to, I don't know, B0. Let's see where this puts him. Oh, look, that's just about perfect. I think it's a little left of center. It needs to go down a bit more, maybe about another 16 rows. So 16 rows would be C0. And we'll move him over, oh, I don't know, 8 more pixels. Okay, I think that's a little too low. I'm going to bring him up a little bit. Now I think he's too far to the right. So we'll go to 124. I'll bring him up to B8. I think that's our winner right there. There's our turtle ship. It's here. It can move back and forth. Now, at the moment, it can also move up and down, but I think I'm going to take that out. I'm going to suppress vertical movement for the moment. Okay, so let's flesh out our control scheme here. So left and right is fine, but we need to put barriers on it. We don't want the player to just go wandering left and right off the edge of the screen. So we need to put a left and right limit on the movement. And I'm also just going to completely get rid of vertical movement altogether. So I'm going to leave the code here because I think we might put it back in. But for the moment, I'm just going to get rid of it. So check vertical is just going to jump back to game loop for the moment. Now, the horizontal, here we go. Move left. This is move right here. So move right is unconditionally moving right, but that's not what we want to do. So when we load player, well, we're always going to do player sub X, I think. No, here's what we're going to do. We're going to load player X. So we're going to put a right boundary on this. In fact, before we go any further, let's actually make constants for these because I think we might need these boundaries for the enemies too. So we're going to make some constants here. Call it left boundary. Let's just put something in there just to see. We'll say, oh, I don't know. Well, here's one way to think about this. So horizontal position 0 for an object is guaranteed to be off screen, even if the object is in quad width. So a quad width object is 32 pixels wide, effectively. So the left edge of the screen is at a minimum 32. So we'll make the left boundary 32, and we'll see how that looks. And then the right boundary, we'll make that, oh, I don't know. I really don't know. We'll put 200 in there to start with. So here, when we try to move right, here's what we're going to do. We're going to load player X, compare it to the right boundary. If it equals the right boundary, we're going to say, nope, you're not moving right, and jump down to check vertical. And similarly, for the move left code, we'll load player X, compare it to the left boundary. And if it equals that, we'll jump down to check vertical. Now, this is assuming that I never move more than 1 pixel on a frame. Or else I would hop over the boundary. I could potentially hop over the boundary. So a better check might actually be BEQ and then also BCC. No, BCS. No. All right, so the better check is right boundary -1. No. The better check is BCS. BCS is going to be, is it greater than the right boundary? So we'll just do it that way. And then down here, the check is going to be not equal, but BCC for less. No, you know what? Never mind. No, these should be equal. Never mind. I'm doing this wrong. So when we do movement, let's put all this back in. Okay. The place to do this is in the movement. So in the movement code, if the movement goes beyond the boundary, you want to set it back to the boundary. That's the way to do this. However, at the moment, we're not moving more than 1 pixel at a time. So if you know you're never going to move more than 1 pixel in a frame, you don't need to do this. So save yourself the time and the space and just don't do it. And for the moment, we're not doing it. So this should lock us down to a left and right boundary. And vertical movement has been disabled. I just checked that. So we go left and, whoa, okay, so that number may be too low. We go right and there. Okay, we hit the right boundary. And that's real close to the edge. I think that's off by like 1 pixel. That was a good guess. The left boundary, however, is apparently completely off. Okie doke. So we need to adjust these boundary values. Let's make the right boundary 201. And let's double this one, because this was way off screen. I have no idea where this was at. Okay, so go to the right and boom. Look at that. Dead on. Okay. Go to the left and okay. So 64 is too far out. So we'll go to, I don't know, we'll try 48. Left, 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 stop. Ooh, did we get it? Yeah, that's spot on. Now, one thing I want to point out, because I just thought of it, is that right now there's a little room around the edges here. So there are 3 playfield modes you can do. I shouldn't use the term playfield modes, because that means something else. There are 3 playfield widths you can select from. And I don't remember which register you go to do this. But right now we're in normal playfield width, which is 40 bytes for a playfield line in this mode. There is also a narrow width, which is less, and an extended width, which is more. So the background color will show in these border areas off to the left and the right. But these areas off to the left and right edge often won't be visible in a lot of TVs. But there's some games you can look at where you'll see the background just kind of extend past everything else. And that's why it does that. I've never used the non-standard width playfields, although I do have a project in mind where I may use the narrow playfield, but I'm not sure yet. I need to decide on it. But there we go. So we got a player anchored on the ground. We got the space turtle. Its movement is restricted on the left and right. So we're close to having something we can work with. Now, let's see what we're going to do now. What do we do now? So we got a player. We can move it back and forth. So I guess now we need to think about what else is this game going to do. So my plan here is to do something kind of similar to Demon Attack, which is why I picked the background that I did. So now that we have our little player and we can move him around, I think next we might need to make him shoot. So we can have him shoot. And once we have him shooting, and that works just fine, we can start looking at enemies. So, how do you shoot? Well, we're going to need two things here in order to make this shoot. One, we're going to need something graphically that we're going to fire. And two, we're going to need the input to shoot, the controller read. The controller read is the easy part. The firing is the hard part. So, let's talk about missiles. So I've probably mentioned a few times throughout this series, there are 8 objects you can place on the screen to work with. Let me put the game back on the screen because I might want to refer to it. So 4 of these objects are called players and 4 of them are called missiles. Just want to check the time. Okay, we're almost an hour into this. So the object we have here, our little pink space turtle, is a player. The 4 player objects are all 8 pixels wide, and they are effectively the entire height of the screen. It's like a big column of pixels. You either turn on or you turn off, which is why there's no vertical position register, because there really is no vertical position, just a horizontal. The missiles work the exact same way as the players, except they're only 2 pixels wide. So they're perfect for something to shoot. I think the idea was we can have 4 players and they each have something to shoot at each other. Great. So what we're going to do is we're going to take a missile and we're going to use it for the player. Now, in terms of color, if we go back and look at the code, I wrote the player's color to this register here. Color PM0. PM stands for player missile. So player 0 and missile 0 are tied together when it comes to color. So whatever color player 0 is, missile 0 is going to be the same color. Whatever color player 1 is, missile 1 is going to be the same color, and so on. Unless there's a special mode, which we might make use of, called 5th player mode, which allows you to set a color an independent color for the missiles. But that color applies to all 4 missiles, so you don't get individual missile coloring. It's just one at a time. We may make use of that here. I'm not really sure, but we'll see. Now, since we have the missile available, I think that's what we're going to use. Now, the way I designed this turtle here, he has a 1 pixel wide nose. So I think the missiles are 2 pixels wide, but I think we're only going to use 1 pixel. And we'll try doing that. So, before we can fire the missile, though, we need some sort of control that's going to check and do it. So here's what we're going to do. So check vertical. Instead of jumping to game loop, we're going to jump to a new label. I'm going to call check trigger. I'm going to put it down here. Well, no, we're going to jump to move done. We already have a label. Move done. Okay, so once move is done, we're going to check the trigger. Now, I'll be back in one moment. Okay, so I forgot my prop again. So here is the Atari 5200 joystick. So in terms of buttons, there are these buttons on the side here. 2 on the left, 2 on the right. Now, the 2 on the bottom on both sides are in fact the same button. They're wired to the same circuit. They're not separate buttons. They're just for left or right-handed people. Same with the button on top. So there are 2 action buttons in effect on the 5200. It's these 2 buttons on the side. Now the bottom button here is the primary button. This is trigger 0, or just trigger. This is trigger. This is exactly equivalent to the 1 button on the 2600 controller, which is what the Atari 8-bit computers use. And you read it the exact same way you read that button on those computers. So how do you read it? whoops, hardware.com. What am I doing? Okay, this is my hardware.s file. We're going to go over here to the GTIA chip. So if you look, this is the GTIA registers. Look here, we have trig 0, trig 1, trig 2, and trig 3. So the GTIA chip reads the triggers. Every other aspect of the controller is read by Pokey. Just this one thing is read by GTIA. And I think the reason for that is because on the A8s, I think that all of the digital control goes through GTIA. Because the original TIA chip in the 2600, I'm pretty sure did all the input. So I think GTIA just kind of inherited that. And since the trigger here is the one aspect of digital control that's still remaining in here, they just left it with GTIA. So you can read from trig 0 at any time to get the state of this button. So if you read from trig 0 and you get a 0, that means the button is being pressed. If you get a 1, or I don't know if it's a 1 or just not 0, but either way, I would do it as just not 0. If you get a not 0, the button is not being pressed. So it's a little bit backwards from what you might think, from like a Boolean logic perspective. But that's how you pick up on that button. So here's what we're going to do. First thing we're going to do is we're going to test the button. So we're going to load trig 0. There's the button. Now remember, if it equals 0, the button has been pressed. So what I'm actually going to do is do the opposite. We're going to branch on not equal to 0 to trigger done. So here's trigger done. So what are we going to do if the button gets pressed? Here's what I'm going to do. I'm going to increment the shadow register for the background color twice. Now the reason I'm going to do it twice is no, I'm going to do it once. Never mind. So the reason I was doing it twice is because the lowest bit of the color codes is not significant. So if you want the color to change, you need to increment it twice. But this is going to happen every single frame that the trigger is down. So it's going to happen so fast that that's not going to be particularly relevant. But what this will do now is once I press the button, the background is going to start changing color. And then when I let go, it's going to stop. So let's see if it works. Okay, I'm going to press the button on my emulator. Look at that. I'm going to stop that. It's annoying. But you see the background keeps changing color. And this is actually a good demonstration of what I was just talking about earlier with the playfield. You see how you can see that dark blue, like the background color on the edges there? Because the playfield's in normal mode. It doesn't extend all the way out. Just an interesting observation. But we're reading the button now. This is the trigger. If it's 0, it's being pressed, and we flash the background. If it's not being pressed, we let go, and it stops. So reading the trigger, reading that button, this is the easiest thing on this controller. It's so easy to read. Right there. You just read the button, you're done. Everything else in this controller is a pain. We've done the easy parts. This button, kind of a pain. These keypad buttons, which includes these up here, start, pause, reset, total pain to read. We will cover that eventually. But if you can restrict your game to just needing the joystick and this one button, do it. Because, I mean, well, you're going to want to do pause and start and reset too. So you can't really get away from those. But, yeah, well, you'll see. We'll get to those. But anyway, so we now have the ability to read the joystick trigger and to do something in response to it. So here's what we're going to do. We're going to create a missile that fires straight up. So we're not going to need to mess with its X position, because what we'll do is we'll set its X position at the time it's fired, and that's not going to change for the entire time it fires. So we're not going to need a variable to store the X position of the missile, because it's just going to go. Like we don't care. It's just, once we set it, it's never going to change. But we are going to need to track the Y position, because we need to move it up. And moving it up means moving it through memory. So we're going to have to do that. So here's what we're going to do. We're going to create a couple new variables. First we're going to do is player shot Y, which we will set equal to 1D. And then we're going to have player shot active. Although, you know what? No, we're not going to do that. We could do that, but we're going to save some memory. We're going to do it a different way. Here's what we're going to do. So, remember now that on the y-axis, which we're just using the memory addresses as the y-axis, higher addresses are down. So the player is at address B8. So the missile is never going to be lower than this address. So what we're going to do is we're going to use a special value. We're going to write FF. We're going to store that into player shot Y. So that's going to be our indication that the player's shot is not currently active, because we only have one missile. Now, we could get real there are fancy tricks you can use here to multiplex the missile and get several shots. We're not doing that yet. Maybe we will later, but for the moment, we're going to just do one shot, and that's what we get back. So if the player shot Y is currently at FF, we're going to interpret that as meaning this shot has not been fired yet. Because we don't want to reset the shot every time you fire. Some games do that. Like Gorf, for example, I think does that, where every time you press the fire button, it resets the shot. That's not what we want to do. You're going to fire the shot, it's going to go, it's going to hit something, and then it'll be reset. So down here now in the trigger code, if the trigger has been pressed, we then need to check to see if the shot is currently active. And if the shot is already active, it's already flying, we don't do anything. So we're going to load player shot Y, compare it to our magic value, which we might want to give a name to. And if it equals that value, we're going to branch to trigger done, because we're not doing anything. The shot's already in the air. We don't care. We're going to ignore it. All right, now I'm going to go grab another cup of coffee, and then we will resume this and actually start working with a missile. Okay. So what do we got here? We have code that detects the trigger being pressed. We have code that detects that the player's shot is inactive or active. So now in this blank space where the cursor is, we need to put the code that's actually going to make the shot appear, that's going to make it active. And then further down, we're going to want to put the code that, you know what, actually, let's organize this a little bit differently. Let's make the very first check to see if the missile is active. So here's what we're going to do. Load player shot Y, compare it to that. If the player shot doesn't equal FF, that means it's in flight. So we're going to branch to move player shot. We're not going to call this, we're not going to call this trigger done. We'll call it player shot done. Yes, we're going to do this a little bit differently. And here we're going to have move player shot. So we're going to only compare this once. So we're going to look at player shot Y. Compare it to that. If it doesn't equal FF, that means that the shot is currently in flight. So we're going to go to move player shot. Then BNE, player shot done. Then we look at the trigger. If the trigger has not been pressed, we just go to player shot done. We're done. But if the trigger has been pressed, we're going to make the missile active. And we're going to make the missile active by putting a different value in there. So here's what we're going to do. Well, we need to set its X value. We need to set its Y value. So its Y value is going to be... We'll make the Y value the same as the player's Y value initially. We might want to make it a little bit higher, maybe. I'm not sure. So the player's Y value... What did we set it to? B8. So B8 is the top of the player. So if we set the missile to B8, it'll start at the top of the player. But I'm doing this in a way where it's going to move 1 pixel immediately. So it's going to kind of end up being one pixel above the player. So we'll load B8, store it in player shot Y. You know what? Actually, we're going to do a little bit differently. B9. We're going to start at no. See, I went the wrong way. B7. So we're going to start at 1 pixel above the player. And then we need to set the X pause. So the X pause, we need to load player X, clear the carry bit, and offset into player X. So player X, if we look at the sprite, this column right here, this is at player X. This is player X plus 1, plus 2, plus 3. So the nose of our space turtle is at player X plus 3. So the missile has to go to that same location. So we're going to load player X, clear the carry bit before we add 3 to it, and store that at HPOS M0. All right, so this stands for horizontal position missile 0. And this is missile 0. So we're going to put the horizontal position of the missile at the exact same place as the player's nose cone or turtle nose or whatever it is. And then we're just going to let it fall through into here, move player shot. So move player shot is going to, move the player shot. You know, never mind. We're going to put this back to B8. Okay, so move player shot is going to move the player shot. For the moment, I think we're going to move it 1 scan line a frame. That's going to be too slow initially. No, you know what? We'll move it. No, I guess we'll move it 2. No, let's start with 1 just to get it working. And then we'll go from there. So this means we need to write the graphics data into the missile zone. So to recap here, let's go back and look at something just to make sure we're clear on how the player missile graphics work. So there's a value up here called PM base right here. And we set this to hexadecimal 10. This is the page number that serves as like the base address for all of the player missile graphics data. This is where Antic looks for the player and missile graphics data. So the page you set here, the first 3 pages at that address are ignored. And I explained last video why I think the reason for that is. So go back and watch that video if you're interested. At page PM base plus 3, so in this case hex 13, that's the missile page. Plus 4 is player 0 page, plus 5 is player 1 page, player 2, player 3, and so on. So all 4 missiles are stored, in this case, on page hex 13. So each byte contains data for all 4 missiles. Now this is different from the player pages, where each byte just contains data for that specific player. But the missiles are packed because they're only 2 pixels wide. So you could cram all 4 of them into 1 byte. So when you're manipulating missile data, you have to be conscious of the other 3 missiles. You don't want to clobber their data while you're moving your missile's data around. So you need to do a lot of bitwise operations here, which I hope you're familiar with, because if you aren't, well, you're about to be. Now, at the moment, there's nothing in this page. We've zeroed it out. But what move player shot is going to do is it's going to erase the missile at the current location. It's going to move up some number of scan lines and write the missile into that location. Now, at the moment, we're going to do one scan line. I think we're going to go faster than that, but we'll see. You know what? Yeah, we'll go one. Right now, we'll just go one. So step one in move player shot. And this is going to be redundant for the frame that the shot is fired. But it's easier to just put this logic in there anyways, do it anyway, because it's going to be harmless. So the first step is to erase the previous missile. Now, these steps could be combined if you really wanted to get fancy and optimize it. There are ways to combine the erasing of the old position and the drawing of the new position. But for the sake of simplicity, we're just going to break them into two discrete steps. All right, so first step is to erase the old missile position. So we got to think now. How tall is the missile going to be? Let's make it 4 scan lines tall for the moment. So here's how we're going to do this. We're going to erase the shot. We're going to load 3 into the Y register, and I'll show you why. Erase missile loop. So, wait, and then I need to... all right. So, here's what I'm going to load into the accumulator. Actually, I need to do this every single time. All right. So, we're going to load... FC into the accumulator. Okay. So this bit pattern, this is all ones except for the last 2 bits, the 2 least significant bits. So remember, all 4 missiles are packed into the same byte. Player 0's missile are the 2 rightmost bits, the 2 least significant bits. That's the player 0 missile data. The next 2 bits over are player 1's, player 2's, and then finally player 3's. So what we want to do here is we just want to erase those 2 rightmost bits. So we're going to load the opposite of that pattern. So it's going to be 1 1 1 1 1 1 0 0. And what we're going to do then is we're going to AND, bitwise AND, with, and here's our little trick, player shot Y indexed by Y. So no, that's not right. Never mind. We need to do this differently. I wasn't thinking right. We need to load X with number 4. We're going to do 4. And then we need to load Y with player shot Y. That was I did this totally wrong. All right. So the missile page is hex 13. So if we index this page with player shot Y, that gets us to the byte where player shot is. This is the top byte of player shot Y. So we're going to take that data, AND it with FC. That'll clear those bottom 2 bits, which will erase player 0's missile while leaving the other 3 completely intact. And then write it back. We have to update the data now. Write it back to 1300Y. Then we're going to increment Y. We need to go to the next byte. Well, we're going to decrement X. So X is keeping track of how many bytes we're going to do. So we decrement X. If it equals 0, we're done. We finished erasing the missile. If it's not done, we need to keep going. So we increment Y. We go to the next byte and then jump back to the erase missile loop. And here we go to erase missile done. Okay, so that little loop is going to go through and erase the prior missile. It's going to erase the missile at its current location. Now we're going to move it up. Now at the moment, we're only going to move it up 1 scan line. So remember, lower addresses are higher on the screen. So to move it up, we need to decrement player shot Y. Actually, you know what? We're going to do this a slightly different way. We're going to load Y. Wait, we already have player, except we incremented it. All right, we're going to load player shot Y again. Decrement it. No, we'll do this a simple way. Dec player shot Y. Load it into Y. We're basically going to do the same type of loop. Again, for 4 bytes. We'll call it draw missile loop this time. Now this time we want a pattern that's going to turn on the 2 rightmost bits. That's going to be the inverse of FC. In fact, that's going to be 0, 3. Because the 2 rightmost bits are 1 and 2. 1 plus 2 is 3. So we're going to take that value and we're going to bitwise OR it with the value that currently exists at 1300Y. So that'll turn on those rightmost bits while leaving the other missile bits alone. And this is the tricky part about working with the missiles, since they're all packed. You can't just go in willy-nilly erasing and writing bytes. You have to get the right bits. And after having ORed it, you need to write the data back. Star. And then the same thing. We're going to decrement X to see if we're done yet. BEQ. Draw missile loop done. Otherwise, in Y and jump back to draw missile loop. Okay, so the one thing we don't have here is something to stop the missile. Oh. Misnamed my label here. Okay, so like I said, at the moment we have nothing to stop the missile. When we fire this thing, it's just going to keep going. So we do need to put in something to eventually stop it. But for the moment, that's fine. So let's run this and see what happens. Now, if an observer might point out there are much easier ways to do this. If you know you're only going to move one at a time, you could just erase the bottom one and put a new one on top instead of erasing the whole thing and then redrawing it. I just erased the whole thing and redrew it for the sake of simplicity. Once we fix on our speed, we decide this is how fast it's going to move, we could write a smarter erase redraw routine that doesn't take as long to do. But this is just for the sake of doing something. So if I press the trigger now, I think we're going to have a missile fire. So let's see what happens. There it goes. And it just keeps going. But you know what? I actually screwed that up. I turned on both missile bits. I didn't mean to turn on both missile bits. I wanted a 1 pixel wide missile. So we need to go modify those values a little bit. And I also see right now that 4 is way too small. I want a bigger missile than that. But first, let's correct those bits. So in the erase loop, well, the erase loop is fine. That's okay. We can erase both bits. That doesn't matter. It's the draw loop that needs to change. So we're not going to do both bits. We're just going to do one of them, the leftmost bit, because I want the missile to be narrow. I don't want a fat missile. So here we go. Shoot. There it goes. There's our missile. Now you notice it's the same color as the player because it shares the player's color register. Okay, so a few things. Although we have a missile, we can shoot it now. There's a few things wrong with it. One, I think it's too slow. And 2, I think it's too short. So we need to make it longer. And I think we also need to make it faster. And then we also need to make it stop at some point and reset the state so that we can do it again. Now, the first thing I'm going to do here is I'm going to do a little bit of code factoring. I'm going to take this erase missile thing out because we're going to need that again. So down here, we're going to create, for now, we'll make it erase. We'll call it erase missile. For now, it's just going to erase the player's missile. I think later we'll expand this and do it in a way that allows us to erase any missile. But for now, we'll just do the player's missile. So erase missile. Let's take this here. All right, this is where we this is where that happens. All right, so let's just yank all this code. And we're going to put it down here. Okay, so we can make these labels less lengthy now because they're they're guarded by subroutines, so we can just call them, we can give them shorter names than what we had before. All right, so we just pulled that out and put it into a subroutine because we're going to need to call that. We need this in two places. We need it, one, where the missile moves, and two, when the missile stops. And the missile is going to stop under two different circumstances. One, when it hits whatever we decide the top of the screen is, and two, when you hit an enemy. So we can't just have a one-size-fits-all missile stop. We have two different checks for when the missile has to go away. So we're going to put this into a subroutine. Now we need to remove it from here now. So move player shot. First thing we're going to do, change this to a jump to subroutine, erase missile. And then this code we can get rid of. Okay. So let's just make sure that worked. So everything should still look exactly like it did, but now we have that factored out into a subroutine that we can reuse. There it goes. Okay, so the next thing I want to do is make the missile longer. So let's go ahead and make a constant for this. Call it missile length. At the moment it's 4. I think 4 is just way too short. We'll make it 12. We'll triple the length. Now, with a length of 12, I might actually want to optimize this and make it more efficient at some point. But for now, we'll just brute force it. So we'll use missile. We'll change this constant to missile length. And then, where's the other place we do this? Right here, where we draw it. I think we'll eventually factor out draw missile too, to allow us to draw any missile. But for the moment, let's leave it where it is. So now we should have a longer missile. It should be 3 times as long. That's better. I like that. That seems good to me. Okay, so next step then is we want to make it faster. So the way to make it faster is right here. So right here we decrement player shot Y. We reduce it by 1 every time. So here's what we're going to do instead. We're going to load player shot Y. Set the carry bit, which you need to do before subtraction generally. We're going to move it, we'll go 2 scan lines at a time. You know what? Yeah, we'll do 2 scan lines. Yeah, if we're going to do 2 scan lines, it's just as easy to deck it twice, and I think it's fewer bytes. So let's do 2 decrements. Because remember, you're moving a pixel at a time. This is going to get fast real quick. I don't want to do sub-pixel motion here for this. That's pretty good. It's looping now. All right. I'm not sure. I don't know. Whoops. Let's see how bad 3 is. This might be too... I have 4. No, I have 3. This might be too fast. But we'll take a look at it. That's fine, actually. Let's go with that. It's going to move 3 scan lines. 3 scan lines a frame. That's fine. So that's 6 bytes there. Each of these instructions is 2 bytes. 1 for the opcode, and this is a page 0 address, so 1 for that. So would it be smaller to actually load it, subtract it, and update it? The load in the store would be 4 bytes. The subtraction would be another. No, it wouldn't. It would be more bytes to load, subtract, and store. So we'll leave it as that. I think that's slower than load, subtract, and store. I'm not sure. Either way, that'll work for now. We don't really care. So now we have erase missile. You know, I am going to factor out draw missile. Let's just get ahead of the game on this one. Because once we start putting enemies in, we're going to want them to have missiles, and at that point, we'll unify these routines to draw any missile. Now, moving the shot, we'll leave that where it is. This code, however, we'll just rip it out. This code needs to go down here. And again, we'll simplify these labels because that's the whole point of the subroutine tag. So not have to come up with unique label names all over the place, because that gets tedious real fast. And we need a return. Okay, so, and now up here, after decrementing the missile, the shot Y thrice, we will jump to draw missile. Or jump to subroutine to draw missile. Okay. So now we should have, nothing should have changed, but we just reorganized. It's got a missile. Pew! Pew! There it goes. Okay, so now that we have those routines isolated, I think we're in a position to stop the missile. So we need to give it an upper boundary. And I think where we're going to do that... Where do we want to do that? So let's see here. Where's a race player shot? Here's where we update it. Okay, I think where we want to do this is after a race, but before we actually change its position. Because we need to erase it every single frame when it's active, whether it's about to go away or not. We still need to do that. So we'll erase it unconditionally. And then right here, before we start decrementing player shot Y. And now, you know, this is going to change this logic too, because now we have to load it anyway. So we might as well do a subtract at this point. So we're going to check the value. So we'll load player shot Y. God, would it be faster to use Y? I think it would be, yeah. Okay, so the fastest way to do this, I think. No, I think it'd be faster to do this. All right, we're going to load player shot Y. We're going to compare it to, we'll make a new constant. We're going to call it shot upper bound. You know, or just upper bound, right? And I think it's going to be a universal upper boundary. We'll compare it to upper bound. Now let's go define upper bound. No, we're going to call it upper boundary, just to be consistent with the others. So upper boundary equals, those are going to be in hex, since we do Y positions in hex because they're memory addresses. Let's pick something here. I have no idea what this is going to be. We're just going to need to pick a value and kind of work toward it. So we'll go with 30 to start with. Hex 30. We'll see where that falls. And then if we like it, we'll keep it. If we don't, we won't. So where do we do this here? Here we go. Compare upper boundary. So we're going to compare the shot to the upper boundary. Now remember, we're moving 3 at a time. So if this, so you know, we want an upper boundary that is a multiple of 3 relative to where we start. So what did we start at? What was the shot? Okay, B8. We start at B8. So let's pick something that is a multiple of 3 from B8. I don't know what that would be. I got to get my calculator open right now. I'm trying to figure this out. So let's go 160 scan lines. 160 is not a multiple of 3, though. The whole thing from top to bottom was, what, 176 scan lines? So if we go 160, that gives 16. And it doesn't start at the very bottom. Let's go with 160. 160, but that's not... No, 150, because 150 is a multiple of 3. So we'll take B8. I'm going to subtract 150. And that leaves us with 22 hex. So we're going to start with a boundary at 22 hex. We'll see how that goes. But if it's a multiple of 3, since it moves 3 pixels per frame, if it's a multiple of 3, we know you're at the end. We know it's going to hit that exactly. Whereas if we pick something else, we need to check if it's gone to it or over it, and it can get messy. So let's pick one where it's going to hit exactly, and we use that as the boundary. So where are we at here? Upper boundary. Where were we doing this? Okay, upper boundary. So we know it's going to be an exact match. So if it does not equal upper boundary, we're going to put a branch to a label we'll call continue shot. And that'll be down here. But we're going to change the way we decrement it. Now, okay, I got to think about this here. So ordinarily what you would do here is you would set the carry bit, subtract 3, and then write it back to player shot Y. But this is one of those assembly optimizations. I got to think here. Do I need to set the carry bit, or is it already set? Because if I load player shot Y, and I compare it to upper boundary, no, the carry bit's actually going to be clear here. So what we could do, this is a clever thing. We know for a fact if we arrive at this label, the carry bit is already clear. If the carry bit is clear and you do a subtract, it subtracts 1 more than what you give it. So what we could do here, to be really clever, is subtract 2 and not set the carry bit. So I'm going to put here a comment. Whenever I do optimization tricks like this, I always like to comment it because sometimes your stuff changes. So carry is set from branch. I hope I'm right about this. Okay, so in the case that the carry is not set, we need to stop the missile. Now, it's already been erased up here. We erased it unconditionally, so we don't need to worry about that. It's gone visually at this point. So what we need to do, though, is write our magic stop value, which was FF, back to player shot Y. And then we jump out, because we don't want to draw the missile again. We jump out to player shot done. So if I've done this correctly, the missile should now hit the top of the screen and stop. Or some defined top of the screen. So here we go. Shoot. And it stopped. That's higher than I wanted it to go. You know what? I think I'm wrong about that carry bit. That missile seems too slow to me. All right, let's not get clever. But one of the great areas of optimization with the 6502 is knowing when you know for a fact that a carry bit has been set or cleared based on the logic around you. You can save cycles and bytes by knowing that. Look at that. Look at that go. Okay, so that's too high because it's going up into the score region. So our math is off a little bit here. So we're going to need to drop the boundary a bit. So the score region is at most 8 pixels high. So let's increase it by 6. So that would make this 28. Okay, I got about half an hour left. Okay, so this I'm hoping is a reasonable top boundary. Shoot. There, perfect. That's excellent. Yeah, I think it might be just barely. No, that's pretty good. That's hitting the bottom exactly. That's perfect. That's exactly where we want it. All right, so now we can shoot. Look at this. We got a guy. We're moving left and right. Our space turtle shooting. We almost got a game here, folks. We got a background. This is getting pretty cool now. All right. So, now one thing I do want to point out is that right now, if you hold down the trigger, it keeps shooting. So if you wanted to make it so that you need to release and press the trigger every time to fire a shot, then you need to have a separate kind of trigger tracking variable. And I do have games that do this because sometimes that's the appropriate thing to do. Where you would have a variable, I guess, that you would track like the last trigger state. And you would only honor the trigger press if the last trigger state was 0, and you would update it every frame. I don't think we're going to do that. I think I'm fine with just holding down the button and letting it go. But that is something you can do if you want, if that's the sort of game you want, and sometimes that is appropriate. You have to set up a separate variable for that and track it. Okay, so we've come quite a long way here today, and I've got about half an hour left. Now, I don't want to get into any more kind of fancy gameplay stuff because I don't think I have enough time to do it. But there is kind of an issue I do want to cover here. And I don't know how long it takes for it to kick in. You know, let's sit here and wait for a little while. We'll just chat. No one seems to be in my chat. Let's go check it out. Who's in my chat? Looks like a bunch of bots. Hey, if anyone in the chat's not a bot, go ahead and say hello, because we're waiting for something to happen here, and I got to kill some time. That's what I thought. They're all bots. So, what I'm waiting for is going to be very interesting when it does actually happen. I can't believe that background came out that well. That's a nice background. I like that. I mean, take a little more work to it, like put some craters on the moon and that, because you could just use the background color for that because you got black. I would probably darken the blue a little bit on the planet there. But yeah, this came out really well. This is a great background. I like this. I just whipped this up in GIMP, like real quick. So the way you want to do this, if you do it in GIMP, is to make... But what I like to do is I make a 320 by 192 image. Or actually, in this case, it was smaller than 192 because I had the top and the bottom rows. The text rows taken into account. But make a 192 by whatever image. Or not, excuse me, not 192. A 320 by whatever image. And then shrink it down to 160. Because the pixels are roughly twice as wide as they are tall. So you do it in 320, and that'll give you an idea of what it's actually going to look like. And then scale it down to 160, but don't use any interpolation. Like, just let it go, like just crunch the pixels. And then you get something that's pretty good. And then you can output that into whatever format works for you. And you're going to need to change it to something the Atari understands, which takes some work. But you can, if you're familiar with any sort of scripting language or anything like that, that's not that hard to do. I just do it in C because I like C. And GIMP can actually output C header files. So I just take that C header and write a program that takes that data and converts it into some kind of data that Anta can actually understand. But yeah, you can use GIMP to whip up images like this pretty quickly. Now, obviously, you can't carry colors for it because you need to set the color registers. But it's not too hard to get something that actually works. I'm hoping what I'm waiting for is going to kick in here any moment now. But it's a common thing that people forget about, and that's why I want to do it now. Because I think, as far as gameplay goes, I think we're at a pretty good stopping point right now. Because we got all kinds of stuff done. We got this background. We got our little player. He's shooting missiles. He's moving. We got the boundaries in place. And this is looking pretty good. This is turning into a real game. I don't think I'll publish this. By the way, in case you don't know, after last week's video, I posted the code up to the point of the video on the Atari Age forums. I have a topic for this series, and I posted the code there. So I'll post the code again for this video, to the point we're at. Probably at the same time the YouTube video goes up, which will probably be on Sunday, maybe Saturday. I have a thing tomorrow, which is Saturday. So I might not get around to it until Sunday, which would be Sunday the 9th. Yeah. And if anyone is attending the Portland Retro Gaming Expo next weekend, I will be at that. You might be able to find me around the Atari Age booth. So if you want to grab me and tell me how great my programming skills are or whatever, hey, do that. Or tell me how terrible they are. If you're an experienced 8-bit programmer from Eastern Europe, where it seems to be very popular these days, go ahead, tell me how much I suck, because you're probably right. Okay, I'm not sure how much longer I'm going to wait for this. What I'm waiting for is something called the attract mode. So let me explain what's going on here. So the vertical blank interrupt in the BIOS, one of the functions it performs, if we go here to the hardware file, on page 0, there's this location called attract. So have you ever seen a 2600 game where you leave it sitting for a while and it starts cycling colors? Now, the reason games did that back in the day was an attempt to prevent screen burn-in on TVs to just change the color and roll them through. Now, the 2600, I believe you had to program that effect yourself. The 5200 does it automatically. And the vertical blank interrupt times this somehow. I'm not exactly sure how it does it. It might be involved the real-time clock things. But this is the final timer right here, attract. So once this reaches a certain value, the vertical blank interrupt in the BIOS is going to start cycling colors on the screen. I don't remember how long the wait is, but it will start eventually. So one of the things you need to do with your program, and make sure you don't forget to do this, is you need to suppress this. Or else people are going to be in the middle of your playing the game, and all of a sudden the colors are going to start going wacko. And you probably don't want that. So I want to show you how to suppress attract mode, which I'm hoping will start here anytime, any moment now. It should be any time now. It should start. But you know what? I can start programming how to suppress attract mode. So to suppress attract mode, you need to create your own vertical blank interrupt. So the vertical blank interrupt comes in 2 steps. So let me sum up how this works. The screen draws from top to bottom, and at the bottom, Antic, or GT, I don't remember which one of the 2, fires a vertical blank interrupt. So the BIOS picks up that interrupt, and it looks at something and determines, hey, this is a vertical blank interrupt. And then it goes to this location here, VV blank I, which stands for vector to vertical blank immediate. And it executes whatever this points to. We send it to VBI int, which is a location in the BIOS. There's a vertical blank handler in the BIOS, and that's generally what you should point this at because it does a lot of important stuff. But the last thing that vertical blank handler in the BIOS does is it jumps through whatever we have at VV blank D. VV blank D stands for vector to vertical blank deferred. So the deferred interrupt handler is for your program to do something else during that vertical blank interrupt period. So if you have something you need to happen every single frame, like clockwork, and the timing for this is important, you set up one of these vertical blank interrupts and you stick it in there. Now, in this case, we have it pointing at a location I call end int, which is an interrupt end sequence in the BIOS. So it ends up just jumping to that and ending the interrupt. But what we're going to do is we're going to write our own deferred vertical blank interrupt handler, and we're going to take care of this attract mode problem, which should be starting any moment now. Come on. All right. Anyway, let's go ahead and start writing that, and I'll leave this running, and maybe at some point we'll see the attract mode kick in. It takes longer than I thought it did. So the first thing we need to do is actually write a deferred vertical blank interrupt routine. And we'll put it way down here at the bottom. So I'm going to call it game v blank. Now, I call it game v blank because in my projects, I typically have different vertical blank interrupts for different phases of the game. Like I might have a game v blank, I might have a title screen v blank, or whatever. So this is specifically the v blank routine for the game. So what we're going to do here is very simple. We're going to load 0. We're going to write it to that attract location. So this is going to reset that attract timer. So every single frame we're going to do this, and this will prevent that attract mode from kicking in. And then to end this, we jump to end int. This is the interrupt ender in the BIOS. So we just jump to that and get, oh, there it goes. Okay, attract mode just kicked in. So you see it's just changing the colors. And it has a formula for doing this. I don't know what it is. I have never written code that properly handles attract mode. I think if attract mode, excuse me, I think if attract mode kicks in, you need to leave it by resetting that timer and then setting your colors back. Or I have no idea how you do it. I just stop it from happening all the time. But it's there, and you need to know about it, because if you don't, this is what's going to happen about 5 minutes into your game or whatever length of time that is. So let's go ahead and kill this now because we've seen attract mode. Okay, so this is our handler. It's very simple. Load 0, store to attract, jump end int. So this is going to happen every single frame. Now, you might think, well, you already have this frame loop, right? Why not put it here? And you could, and it would work. The problem, though, is that in more complicated games, you're going to have more than one loop. Like in my game, for example, I have, like in Robin Banks, I had several loops for several different states of the game. So I would have to do that in every single loop, which is a waste of space. And I also have to remember to do it in every single loop. But if you put it in the v-blank interrupt, it applies to everything, so you don't need to remember to do it. Now, you might make an argument for once the game is paused, you might want to let that happen. I don't do it. I mean, you could. So now we have our game v-blank. Oh, I want to point out one other thing. Okay, so I reserve game v-blank for things that need to happen on every single frame and the timing is important. So the big thing that I put in here is anything involving sound. Because your sound processing, and sound is probably going to be one of the last things we get to because sound is really complicated and I don't know a lot about it. But sound processing is very sensitive to time. So you want to make sure that's happening on a regular beat. And I put all the sound processing into game v-blank. But we'll talk about that later. So we now have our game v-blank. So we need to set it up to point to our deferred v-blank. So that is this vector here, v-blank d. So right now we're writing end into it. We're going to pull it out of there. We still want the keyboard interrupt to go there. But here's what we're going to do. Okay, so we'll load the low byte of our v-blank, which is game v-blank. Store it to v-blank d. Load the high byte of game v-blank. Store it to v-blank d plus 1. Okay, so now, oh, we got a problem here. Oh, I typoed that. All right, so now what we should have is our vertical blank interrupt should be firing, and it'll suppress a track mode. Now, I'm not going to sit here and wait for a track mode to run. I just want to make sure everything was cool. But we should probably verify that that vertical blank interrupt is actually running. And the way we're going to do that is by putting something in here that we can actually see happen. So we're going to go with the good old increment the background trick. So every frame we're going to increment color the background, and we'll watch the fireworks. And this is just to verify that that vertical blank interrupt is in fact running. There it goes. Okay, and we'll stop that before people have seizures. So, this vertical blank interrupt is now running. Look at that, we did an interrupt handler. Sort of. Okay. So this might be about where I want to stop for today. So let's sum up. What did we get done today? Okay, so we got a background. We got kind of a game screen built. So this is the first day where we have something that actually looks like it might be a game. You know, we got through the preamble and explaining how the hardware works, and now we're actually doing something. So we got this fantastic background image up here. I had to go through the whole thing about how Antic can't hop over 4K boundaries, and how annoying it is, and we fixed that problem. We got a little player ship sea turtle thing here moving around on the moon with right edge boundaries. We took away vertical movement for now, so it's just horizontal. We added this cool missile, which not only fires, but has a boundary and comes back. We added a trigger. We can detect the button now. So we got a lot of pieces in place here. And it's going, it's going, it's going. I might want to move the starting position of that up a little bit. But that's something for another time. But, you know, hey, we're getting close. We almost have a working, like something approaching a functioning game here. So I think what we'll do next week is I think we're going to have two major goals for next week. I think one is to clean up the top and the bottom lines. So right now, the top and the bottom lines, which are the text lines we put in there, are just gray. And that's because of the way colors work in those lines. Now, to fix this problem, we're going to need to use something called the Displayless interrupt. This Displayless interrupts, I think, are probably the most complicated topic on the 5200. This is where things get a little thorny. And is why I didn't want to do it right away, but I think this is probably a good time to do it. So I think that's probably what we'll start with next week, is with Displayless interrupts. And we'll show how to clean up the top and the bottom lines there. And we'll probably throw some text in there just so we can see it, and have something to look at so we know that those lines are there, because otherwise they're just going to be black. But I think that'll be the first topic for next week will be Displayless interrupts. And then once we have that, I think maybe we'll start putting together some enemies. And once we have enemies, we need to start putting in some more fairly detailed game logic. I mean, right now we have the missile logic, right? Shoots, stops, comes back. That's great. But we have to put the enemies in. We have to decide what they actually do. So I think we're going to have very few enemies because we have the other 3 player objects. So I think what we're probably going to do is just use the other 3 player objects. So we'll just have 3 enemies up there. And they'll be bombing us with missiles. So we'll take the other 3 players and the other 3 missiles and put them to use as enemies up top and let them rain fire down on us. And we'll see how that works out and how it goes from there. But yeah, I think this has been a pretty good session. We accomplished everything I wanted to accomplish. And in the longer term, I have some more ideas I want to add to this. But I'm not sure how far I'm going to go with this game, because this is more about just illustrating certain concepts and stuff like that. So I'll probably get to a certain point. I'll post the code on Atari Age. Hey, if you want to take this game and just run with it and start doing stuff with it, hey, go for it. Please do it. Yeah, whatever. But I would like to actually start working on another project on this series to look at that I can use to demonstrate some of the other more interesting Antic modes. Because right now we're really just using text mode and bitmap mode. There are some crazier modes that a lot of games make use of. And it's important to understand how those modes work, because you might want to use them. But I think that for now, this is probably a good stopping point. So we'll stop here, and I'll probably post this video up on YouTube within a couple of days, and the code to the Atari Age forums. And next week, we'll get back to this, and we'll see what else we can figure out. So thanks for watching, and tune in next week for more exciting Atari 5200 action.